Hello everyone, and welcome to this video on orthogonal sets. So in this video I'll start off by defining what it means for a set of vectors to be considered orthogonal. In the last video we talked about just a pair of vectors being orthogonal. In this video it's an entire set of 7 vectors, 8 vectors, k vectors being considered an orthogonal set. And then on top of that, I'll define what it means for a set of vectors to be orthonormal. Right? Not just a pair of vectors, but a set of 2 or more vectors to be considered orthonormal. And then I'll go through several examples in which I'm given a set of vectors from some inner product space, and I'm asked to determine whether or not that set of vectors is orthogonal, orthonormal, or neither. Alright. So, what does it mean for a set of vectors to be orthogonal? So a set S containing vectors, say v1, v2, all the way up to say vk. A set of vectors in an inner product space V is called an orthogonal set, right, or is just orthogonal, when every pair of vectors in S is orthogonal. Now remember, what it meant for a pair of vectors to be orthogonal was that their inner product was 0. So another way of putting this is that the inner product of V sub I with V sub j will be equal to 0 whenever I is not j, right? That's what I mean by every pair. So if I do the inner product of V1 with V2, it'll be 0. V1 with V3, it'll be 0. V2 with V3, it'll be 0. V1 with VK. As long as the vectors are not the same vector, right? I'm not doing V1 with V1 here. I'm not doing V2 with V2. So as long as every pair of different vectors in the set is orthogonal, then the entire set itself will be considered an orthogonal set. Now, if you have an orthogonal set of vectors, the question to naturally ask right after that is the set of vectors orthonormal? So if, in addition to this, right, if you have an orthogonal set and each vector in that set is a unit vector, then the set S is also called an orthonormal set. Right? They just say S is orthonormal. So an orthonormal set is an orthogonal set, right? Every pair of vectors that aren't the same will have an inner product of 0. And on top of that, in an orthonormal set, the norms of every vector will be 1. Right? Every vector is a unit vector in the set. So the norm of v1, the norm of v2, all the way up to the norm of vk will be the number 1. Right, and if you find any vector whose norm is not 1, then you can't have an orthonormal set. Okay, so the rest of the video is just me going over several examples where I have a set of vectors from some inner product space, right, where an inner product is defined, a proper inner product. And I'm simply asked, is that set of vectors orthogonal, orthonormal, or neither? Okay. So, like I said, the instructions are determine whether the set S is orthogonal, orthonormal, or neither, with respect to the given inner product. Right. So here I have a set S of a few vectors from R3, right? Each one of these has 3 components. 4, negative 1, 1, negative 1, 0, 4, negative 4, negative 17, negative 1. And these are vectors in R3, let's say with the inner product being the dot product, right? The standard inner product or the Euclidean inner product, right? The dot product is my inner product for this example. All right, so let me label these. All right, I have a set with 3 vectors. Say this negative 4, negative 1, 1 is vector v1. The negative 1, 0, 4 is vector v2. And negative 4, negative 17, negative 1 is vector v3. So what we have to do to check for, is the set orthogonal, is I have to look at each pair of, different vectors, each pair of vectors in this, and see if they're orthogonal. Is their inner product equal to 0? So I have to check each pair. So first I'm going to take the inner product of v1 with v2. Now the inner product here is again simply the dot product, right? Just as you've seen in previous videos, you have to really pay attention to what the inner product is, right, when talking about orthogonality and norms and stuff like that, and distances. All right. So v1 was this vector here, v2 was this vector here, and the dot product is simple, right? Just multiply corresponding components and add those products, right? So 4 times negative 1, the product of the first components of v1 and v2, plus negative 1 times 0, plus 1 times 4, and that's negative 4 plus 0 plus positive 4, that is 0. Okay, so far so good. Now, this tells me that these two vectors are orthogonal, but it doesn't tell me that the set is orthogonal. Okay, so we have from this line, v1 is orthogonal, right? I'm using that is orthogonal to kind of like the perpendicular symbol just to save some writing. These two vectors are orthogonal, but that doesn't mean the entire set is, right? For the entire set to be considered an orthogonal set, every single pair of vectors has to be orthogonal. So that was v1 with v2. Then I'll check v1 with v3. So what's the inner product of v1 with v3? All right. So again, looking at v1 here, v3 there, the inner product is simply the dot product again. So we have 4 times negative 4 plus negative 1 times negative 17 plus, and then 1 times negative 1. And that's negative 16 plus 17, which is positive 1, plus negative 1, which is 0. Great, so I have, v1 is orthogonal to v2. v1 and v2 are orthogonal. v1 and v3 are orthogonal. And then the only other pair that I haven't checked are v2 and v3, right? I've done v1 and v2, v1 and v3. But the only pair I need to check now is v2 and v3, right? So you can probably see how this will be a bit tedious when there are more and larger numbers of vectors in your set. Right, with the 3 vectors here, I only need to do 3 pairs. But if you'll see in the next example, I have 4 vectors, and if you have 4 vectors, that there's a total possible number of 6. There are 6 pairs of vectors that you need to check the inner products of. And so we have checking the inner product of v2 with v3, and the inner product is simply the dot product. Here's v2, here's v3. So we have negative 1 times negative 4 plus 0 times negative 17 plus 4 times negative 1. So we have positive 4 plus 0 plus negative 4, and that is indeed 0. So I've checked all possible pairs of different vectors, right? I'm not doing v1 with v1 or v2 with v2, right? Because remember, for an inner product of a vector with itself, if that vector is not the zero vector, you're going to get a non-zero quantity. But we're just checking the different pairs of vectors. So we have v1 and v2 are orthogonal, v1 and v3 are orthogonal, and v2 and v3 are orthogonal. So every pair of vectors is orthogonal. Every pair of vectors in this set, every pair of vectors in S is orthogonal. So they would say that the set S is orthogonal. Right, so S, the set S is orthogonal. Great. All right, and then the question that arises from that, if a set of vectors is orthogonal, like my set S is here, the question that naturally follows is the set orthonormal? And it's real simple to answer that one. Just find the norm of each vector. And if the norm of each vector is 1, if they're all unit vectors, then the set is orthonormal. And if one of them has a norm that's not 1, then it's not orthonormal. Very simple. So I'll take that to the next page, right? So is S orthonormal? Right. Now be careful, you should only answer this question, orthonormal with an R there. You should only answer this question after you've determined that the set is orthogonal, right? Because if the set is not orthogonal, it can't be orthonormal, right? An orthonormal set has to first be orthogonal, right? Every orthonormal set is orthogonal, right? But not every orthogonal set is orthonormal, as we'll see in a second here. So to answer this question, like I said, we're going to find the norms. Right, the norms, or the magnitudes of each vector. Alright, so again, back up here, I know the set's orthogonal, so now I'm just going to find the norms, see if it's orthonormal. Alright, what's the norm of vector, v1 there? Now remember how to define the norm in an inner product space. The norm of a vector was the square root of the inner product of that vector with itself. All right, but here the inner product is the dot product, so I'm taking the square root of the dot product of v1 with itself. So that'd be, the square root of, 4 times 4, or 4 squared, plus, -1 times -1 squared, plus, and then 1 squared, right? Just squaring the components. Right? The dot product of a vector with itself is just the sum of the squares of the components of that vector. And we're very clearly seeing that this is not 1, right? This is 16 plus 1 plus 1. This is the square root of 18, or 3 times the square root of 2, which is not 1. Right. Square root of 18, 3 times the square root of 2. So v1, right, this vector with components 4, -1, 1, under the dot product, under this inner product, we're seeing that vector 1 is not a unit vector under this dot product, right, under this inner product. So we don't need to check the other two. Right? We don't need to check the other two. We have shown that not all of them, right, are unit vectors. So I can very easily say now that S is orthogonal, sure. S is orthogonal still right? Every pair of vectors is orthogonal under this inner product, but S is not orthonormal. Okay. Now, if you'd like to make an orthogonal set into an orthonormal set, you just simply need to normalize the vectors. Right? And that was by just, and I've done this in previous videos, so again, hopefully you've been watching, following along. You just multiply each vector by the reciprocal of its norm. All right, so let's say, all right, now the question's over. Right? I already told you that this set of vectors under this inner product, the dot product, it is orthogonal, right? But not orthonormal. Right? But what if I asked another question after this? All right, so say I take the same set with the same inner product, right? The same set under the dot product, and now I said, all right, find a set of vectors. Find a set of vectors that is orthonormal. Using S here. All right, and I'll make a little note here describing what we're doing, and I've said it out loud already. So to transform an orthogonal set into an orthonormal set, to transform an orthogonal set into an orthonormal set, normalize each vector. Right, just multiply every vector by the reciprocal of its norm to turn it into a unit vector. Right, normalize each vector. Right, so remember, this requires finding the norms. Now I've already found the norm, right, the norm of vector 1. That was the square root of 18, or 3 times the square root of 2, under the dot product, right? Now I could very easily do the other ones, right? The norm of vector 2 is going to be the square root of, again, just the dot product of the vector with itself, so 1 plus 0 plus 16. This is square root of 17, the norm of vector 2. Again, that's not 1, so again, we don't, neither of these are unit vectors right now. And the norm of vector 3 is, now this one's a little hairier, but I'll punch this in. All right, so we got 4 squared is 16. All right, so clear that. So I don't know why I'm putting 4 squared. I know it's 16. Negative 4 squared is 16 plus, negative 17 squared. That'd be, 289. And then plus 1, right? So 306, right? 306. I think 9 would go into this, right? 34 times. So this is 3 times the square root of 34. The square root of 306 you could write as the square root of 9 times the square root of 34, 3 times the square root of 34. Alright, so I have the norms of each vector. Now I just need to simply multiply each vector by the reciprocal of the norm. Right? So I'll get this new set called, I'll call it S prime. Right? So this was S. This is S prime, totally different set. But it's just going to be made up of the vectors where, I take vector v1 multiply it by the reciprocal of the norm of v1. So 1 over 3 times the square root of 2 times vector v1, 4, negative 1, 1. And if you can multiply each component by the scalar and get 4 over 3 root 2, negative 1 over 3 root 2, and 1 over 3 root 2. And you would see that the norm of this vector would be 1. This is a unit vector. And the same thing for v2. I'm going to multiply v to turn it into a unit vector. I'm going to multiply it by 1 over the square root of 17. So the second vector, 1 over the square root of 17 times the vector negative 1, 0, 4. There's another unit vector. Again, just you can put the scalar in if you wish, right? That'd be negative 1 over root 17, 0, and then 4 over the root 17. And finally, do the same thing to v3. Right, take vector 3 here, multiply it by the reciprocal of its norm, 1 over 3 times the square root of 34, multiplied by the vector v3, negative 4, negative 17, and negative 1. And this would be another unit vector, right? Again, if you multiply each component by that scalar, you get another unit vector. So this set of 3 vectors S prime under the dot product, I had a set that was orthogonal already. I just turned all the vectors into unit vectors. So this is an orthogonal set of unit vectors, otherwise known as an orthonormal set. So this set here, S prime, is an orthonormal set. So hopefully looks pretty simple, right? If you have an orthogonal set already and want to change it into an orthonormal set, just normalize each vector, multiply each vector by the reciprocal of its norm under that particular inner product. Great. All right. Well, let's go back to the original instructions, right? Let's just determine whether a given set S is orthogonal, orthonormal, or neither for the next example. All right, my next example, I have a set with 4 vectors. All right, and these are vectors from R4. All right, notice they all have 4 components. So 3, 4, 0, 0, negative 1, 1, 0, 0, 2, 1, 0, negative 1, 0, 1, 1, 0. So this is a set of vectors in R4. Let's say with this inner product. Now notice that this is not the dot product. It's not the dot product. It's one of those weighted Euclidean inner products where the weights are 4, 3, 1, and 1, right? The coefficients on the U1, the product of the first components, the product of the second components, product of the third components, and fourth components. The coefficients are not all 1. All right, so this is one of those weighted Euclidean inner products on R4. All right, so let's determine if this is an orthogonal set. All right, so again, I'll label these. There are 4 vectors in here. Say vector v, v1 for vector 1, v2, v3, and v4. And when I'm asking, is the set orthogonal, I have to check each pair. So let's check the pairs for orthogonality under this inner product. Again, keep, every time, pay attention to how the inner product is defined. So I'll start with v1 and v2. Right, the inner product of vector 1 with vector 2. All right, and then, like I said, there's going to be 6 pairs here. Now, I might not have to do all 6. Right? As soon as if all of them are 0, great. Then we have an orthogonal set. As soon as I find an inner product that's not 0, then I don't have an orthogonal set, and I can stop. Right? Every inner product of every pair has to be 0 for the whole set to be considered orthogonal. So can you count them, right? See I have v1 with v2, v1 with v3, v1 with v4, then v2 with v3, v2 with v4, and v3 with v4. Right? There'd be 6 pairs. that I would have to check if they all end up being 0? Let's see. What's the inner product of v1 with v2? Well, it's again, according to this rule here, it's 4 times the product of the first components. So 4 times 3 times -1. That's for v1 and v2. Plus, and then 3 times the product of the second components. So 3 times 4 times 1. Then plus the product of the third components, which are just 0 and 0 for v1 and v2, plus the product of the fourth components, which are again just 0 and 0 for v1 and v2. So I have 4 times 3 times -1, that's -12, plus +12, which is 0, and then plus 0 plus 0, this is 0. So under this inner product, under this inner product, vector v1 is orthogonal with vector v2. Right? This pair of vectors is orthogonal. Now be careful, right? Just because you found one pair that's orthogonal doesn't mean that the whole set is orthogonal. Right? You have to every single pair needs to be orthogonal. So that was v1 with v2. So how about v1 with v3? Right, so same deal. Now v1 is this one with the 3, 4, 0, 0. v3 is this vector with the 2, 1, 0, -1. So the inner product of v1 with v3 again is 4 times the product of their first components, right? So 3 and 2, 4 times 3 times 2, plus 3 times the product of their second components, so 4 times 1 for v1 and v3, plus then the product of their third components, which for v1 and v3 are both 0 here, right? Plus the product of their fourth components, which for v1 and v3 are 0 and -1. All right, let's see what we get. 4 times 3 times 2, that's 24. All right, 12 times 2 is 24. Plus 3 times 4 times 1 is 12. 24 plus 12 is 36. 36 plus 0 plus 0. This is 36. That is not 0. So, under this inner product, vectors v1 and v2, v3, v1 and v3 are not, a little slash through this, not orthogonal. And if you find, so I can stop now. All right, I know I said there'd be 6 pairs. But that's only if you actually have keep finding 0 as your inner product. You have to check all 6. But as soon as you find one pair of vectors in the set that aren't orthogonal under the inner product, then the set is not considered orthogonal. So S here. And if it's not orthogonal, it can't possibly be orthonormal, right? Because again, in order to be orthonormal, you have to be orthogonal and have unit vectors, right? So S is neither orthogonal nor orthonormal, right? Because again, if you're not orthogonal, you're definitely not going to be orthonormal. And that's as soon as you find a single pair of vectors that aren't the same vector, right, where the inner product is not 0, you find a pair of vectors that's not orthogonal, then the whole set is not considered orthogonal, and therefore not orthonormal, as I've said. All right, so again, hopefully pretty easy example. And since it's not orthogonal, right, I can't just multiply by the reciprocal of the norms to make it orthonormal, right? I can't turn this into an orthonormal set by just simply multiplying by the reciprocal of the norms. All right. it's not like my first example, right? If you have an orthogonal set, you can do that. But if the set's not orthogonal, right, I can't just multiply by the reciprocals of the norms and change them all to unit vectors and have it be orthonormal, because they're not orthogonal in the first place. Okay. I have one final example. Again, I'm not going too crazy with these. You'll see hopefully plenty in practice problems you're working on with different inner products over different vector spaces. So I have an inner product here over a vector space that's pretty similar to the dot product. All right, so here S is a set of polynomials, right? The polynomials 1, x, and x squared. And these are polynomials in P2. Remember, this was the vector space containing all polynomials of degree 2 or less, with standard polynomial addition and scalar multiplication. And the inner product I have defined here is the inner product of two polynomials is the product of their constant coefficients plus the product of their linear coefficients plus the product of their quadratic coefficients, right? I've mentioned down here that p of x is a0 plus a1x plus a2x squared. So a0 and then q of x is b0 plus b1x plus b2x squared. So a0 and b0 are the constants. A1 and B1 are the the coefficients of x to the first. A2 and B2 are the coefficients of x squared. All right. So under this inner product, is this set orthogonal? All right. So just as my first example, this one has three vectors, right? Vector 1 is the polynomial 1. I'll call that V1. Vector 2 is the polynomial x, right? And vector 3 in this set is the polynomial x squared. Now to check if they're orthogonal, right, I'm taking inner products, right, based on the definition of inner product over here. So I'm checking each pair. Now, as with the first example, there's only three vectors in this set, so there are only going to be three pairs I need to check. And I might not even do all of them, right, if I find an inner product that's not 0, like the last example. So what's the inner product of V1 with V2, right? So what's the inner product of the polynomial 1 with the polynomial x? All right, so again, based on the definition of the inner product here, all right, it's the product of the constant terms. That's just a0, b0. So 1 times 0 plus the product of the coefficients of x. So there's no x in this polynomial, so 0 times and then 1x here. So 0 times 1 plus, and then the product of the x squared coefficients. Well, both of them have 0x squared, so we have 0 times 0. And can you see this is just 0, right? So under this inner product, right, vector 1, right, the polynomial 1, and vector 2, the polynomial x, are orthogonal. Right? But that's just one pair, right? I got to do all pairs. Check all pairs. So how about instead of V1 with V2, now how about V1 with V3? I'm just being very methodical here. So that's the inner product of 1 with x squared. Right. So again, pretty simple. What's the product? It's the product of the constants first, so 1 times 0 plus the product of the coefficients of x. Well, neither of them have an x in it, so 0 times 0 plus the product of the coefficients of x squared. There's no x squared in that one, 1x squared in that one, so 0 times 1. And yet again, hopefully you're seeing this is 0 plus 0 plus 0, or 0. Wow, okay. So the polynomial 1 and the polynomial x squared, which I called V1 and V3, those are also orthogonal. So far so good. I just got one final pair to check. Right? You got to do every pair if necessary. So that's V1 with V2, V1 with V3, all it's missing now is v2 with v3. Or, the inner product of x with x squared. Okay. So again, the way the inner product is defined is the product of the constants, which both of them have a constant of 0. So 0 times 0 plus the product of the coefficients of x, 1x, no x, so 1 times 0, plus the product of the coefficients of x squared. There's no x squared there, 1x squared there, so 0 times 1. And again, I'm getting 0 plus 0 plus 0. So fantastic, right? Absolutely wonderful. v2 and v3, right? This polynomial x and x squared are also orthogonal, right? So every pair, sorry, that says every pair is orthogonal, right? Fantastic. So we can say right now that S is an orthogonal set, or just plainly S is orthogonal. Now if it's orthogonal, again, the natural question to ask is it also orthonormal? Are each of these vectors, each of these polynomials, unit vectors under this inner product? So now let's find the norms. So I'll go to the next page. So now let's find the norms under this inner product and see if this set of vectors is orthonormal. Alright, so what's the norm of vector 1? What's the norm of vector 1, or the norm of that polynomial 1? Alright, remember, the norm of a vector is defined in an inner product space as the square root of the inner product of that vector with itself. So this would be the square root of, the inner product of 1 with 1. Well, the inner product of 1 with 1 would be, 1 times 1 plus 0 times 0 plus 0 times 0. So that's just the square root of 1, which is 1. Hey, so far so good. The first vector is a unit vector. It has a norm of 1. Right, but I need all vectors in the set to be unit vectors in order for this orthogonal set to be considered orthonormal. How about the norm of v2, right, or the norm of x? Well, that would be the square root of the inner product of x with itself. And you see that would be, according to this definition, 0 times 0 plus 1 times 1, right, they're both 1x, plus 0 times 0. So again, I have the square root of 1, or just 1 again. Hey, fantastic. This second vector, the polynomial x, is a unit vector. So, so far, so good. Right, but the third one could fail. Right? You're probably seeing that it doesn't. It doesn't fail. It actually is a unit vector. So let's find the norm of v3, the norm of x squared under this inner product. So the square root of the inner product of x squared with itself. And following this definition of the inner product here, it'd be 0 times 0 plus 0 times 0 plus 1 times 1. Right? They're both 1x squared. So that's the square root of 1 times 1 again. The square root of 1 or just 1. All three pretty simple. Right, so v3 is also a unit vector. Right, so so it's an orthogonal set first off. Right, we showed it was an orthogonal set. Every pair of vectors was orthogonal. So it's an orthogonal set, and on top of that, every vector in the set is a unit vector under this inner product. So by definition, this set is orthonormal. So this set S is orthonormal. And that's wonderful. So again, pretty simple, right? Just if you're given a set of vectors in some inner product space, first pay attention to how the inner product is being defined. All right, then take the inner product of each pair of vectors in the set. Now again, the more vectors there are, the more pairs you're going to have to take. And as soon as you come across an inner product of a pair that's not 0, you can stop and say, hey, this set is not orthogonal, and therefore not orthonormal either. But if it is orthogonal, right, if the inner product of every pair is 0, then to answer the orthonormal question, you must find the norm of each vector, which is again the square root of the inner product of that vector with itself. And if you ever come across a norm if you have an orthogonal set and one of the vectors has a norm that's not 1, then it's not orthonormal. But if all the vectors in an orthogonal set have a norm of 1, then that set is orthonormal, as we saw in this last example. And then, like with my first example earlier, if you have an orthogonal set that is not orthonormal, but you'd like to transform it into a set of vectors that is orthonormal, you take that orthogonal set and just simply normalize each vector. You multiply each vector in the orthogonal set by the reciprocal of their norms, and that'll give you a set of vectors that is orthonormal. Okay. But again, don't do that if the set's not orthogonal. That won't do anything. That'll just give you unit vectors, but they won't be orthogonal. Right? Orthonormal set has to have both. Right? It has to be an orthogonal set, and have all these unit vectors in it. Great. All right. So hope you found this informative, easy to follow, and I hope you enjoy practicing problems like this where you're given a set of vectors and asked if it's orthogonal, orthonormal, or not. And thank you very much for watching.